All right, so very important concept being discussed today. This is the concept where a lot of students are weak, and I'm giving you the basics, but you must know these basics to strengthen your semiconductor chapter. So let's start with how the conduction happens in intrinsic semiconductors. What are intrinsic semiconductors? I believe you know that. So pure semiconductors are the, for example, silicon and germanium, right? These are the intrinsic semiconductors. Very fundamental point, but you must know. Intrinsic semiconductors. Okay. How do they conduct electricity is the question. Let me just draw a diagram. So let's say you have a silicon atom. Okay, this is silicon, and it forms a bond with another silicon. It has four valence electrons, and it is surrounded by the silicon everywhere. So this is pure. So this is also silicon, right? These are covalent bonds which this silicon has created with the neighboring atoms. And this whole structure is called as a, if you don't understand, let me just complete the diagram first. So this is your silicon atom. So four valence electrons, each has a four valence electrons. You can see the central one I have drawn. So, this is electron number one, two, three, and four. So four valence electron. And similarly, each of the neighboring silicon atom also offers its own electron to the bond. So this particular silicon atom has offered this electron, right? So that's the way you create the bonding, the covalent bonding in silicon. Okay. Now what happens is, let me just draw the energy band diagram for an intrinsic semiconductor, which is what will teach you, the exact way it conducts electricity. So this is your, I'm drawing the energy band diagrams, and then I'm drawing, okay. So all the electrons which you see, okay, this is 0 Kelvin. Temperature is very important for you to understand that whatever I'm teaching you is at 0 Kelvin right now. The electrons which are part of the covalent bonds all are residing in a place which is called as the valence band. So it's a band of energy, which is this band of energy. It's called a VB, okay, the valence band. Okay, then there is a gap, which is the forbidden gap. This is the forbidden gap. Okay, and then there is another band of energy, which is the conduction band. Okay, and this is where, so let me just complete the diagram. Okay, so this is your conduction band. Okay, this is your conduction band, or it's also known as CB. Okay, so CB is mentioned here. And this is the forbidden gap, the forbidden gap, forbidden gap. Now, most of the electrons which you see in this diagram, so you see this bond diagram, right? So this is your bond diagram. It shows the bonding between the silicon atoms, right? So if you see this bond, the electrons that you see which are part of the bonding, okay, each of the silicon has created a bond with a neighboring atom. Okay, this is silicon, this is silicon, they share electrons, and this is what the bonding is all about. Now the forbidden gap is there, and the electrons which you see as part of the bond are the valence band electrons. They are all residing in this band. Okay, so all the electrons which are part of the valence band or the covalent bonds are residing here. Okay, are residing here. This is where it resides. And again, The diagram I have drawn is the energy diagram. The energy diagram, and this is at 0 Kelvin. Now what you do is you increase the temperature of your room. I said the room temperature should be increased to a level of 300 kelvins. Okay, this is like 27 degrees, uh, the room temperature. So let me redraw the diagram and tell you what happens. If I redraw this diagram of the silicon atoms, there is a surround, no, neighboring silicon atom, and then they share a bond. So let me just, so this is silicon, this is silicon, this is your neighboring bond, and then this is your neighboring bond, this is your neighboring bond, and this is the silicon atom, right? This is silicon, this is silicon, right? Now what happens? The When the temperature is 300 Kelvin, okay, when the temperature is 300 Kelvin, these electrons which are part of the bond, okay, so for example, this particular electron, let me just show you with the help of some different color. This particular electron, right, will break out of the valence bond, okay, and become a free electron. So this will break out of the lattice, and this can move anywhere in the lattice, in the structure of the silicon. So this has become a free electron. Okay, some will break away, some will definitely break away, not all. Very few electrons have the power or get sufficient energy to break away from the parent silicon atom. And once they break away, what happens is, in terms of energy diagram, if I were to tell you, let me draw this diagram again. So let me just draw this diagram. I will show you what happens. Very important conclusions to be drawn today. And this is your, the diagram, and this is your, diagram. Okay, so the electrons which were residing here, okay, I said so these are valence band electrons. But now this diagram I am drawing, the energy band diagram, is now at 300 Kelvin. So new diagram is at 300 Kelvin, and some of the electrons have broken out of this. Okay, I've just shown one electron. You can show, one more electron, maybe, it breaks out. So one more electron breaks out of this. All right. Now let me just complete the diagram, which is the energy diagram. So you can see these electrons which are part of the valence band. Okay, these are part of the valence band. Okay, I'm just filling up the valence band, and this is the valence band. This is the forbidden gap. Okay, this is your conduction band. Okay, this is your conduction band. Now when the temperature is 300 Kelvin, the electrons in the valence band, what happens to them is they jump to the conduction band. Okay, only few. So few electrons jump here. Okay, so the electrons have reached the conduction band. Okay, and conduction band electrons are the ones that take part in flow of current or electricity. When they move here, what happens is what they leave behind is a hole. So let me just remove these two. Okay, let me just remove these two. I will draw the band line again. It got rubbed off so that you don't get confused. Okay, so those two electrons left and they have moved here. What they leave behind is the hole. Okay, let me show you the two holes that got created because of that movement. Okay, the electrons moved to the conduction band and left valence band holes in the valence band. So these are the holes. These are the holes. Now, can you see there are two electrons that actually jumped, like this. Okay, so these are the electrons in the conduction band now. These are electrons in the conduction band, and they left behind two holes in the two holes have been left in the valence band. So just mind you, at 0 Kelvin, the pure semiconductor during 0 Kelvin is not able to conduct any electricity because all the electrons, you need electrons for flow of electricity, but they're all bound, right? So if you see this bond diagram, all the electrons are bound to each other as part of the covalent band. So these are bound electrons right now. If I were to say, these are bound electrons. And so all the electrons at 0 Kelvin, all the electrons which you see, right, where are they residing? Are in valence band. But if you look into 300 Kelvin diagram, now the electrons have moved to the conduction band also. So at 0 Kelvin, when all the electrons are in valence band, no electricity flows because this is empty. Okay, this is completely empty. There is no electron. No electrons are there. No electrons. So if you have no electrons in a conduction band at 0 Kelvin, no electricity flows, right? So conduction band is absolutely empty. So it's an empty one at 0. But at 300 Kelvin, some electrons have jumped to the conduction band and now they are capable of being part of current and electricity. Okay, so they will allow some conduction. So if you find that the intrinsic semiconductor at 0 Kelvin is practically behaving like an insulator, uh, and but if you raise the temperature of the intrinsic semiconductor, which is your pure semiconductor, and increase it to 300 Kelvin, you will find that electrons have reached the conduction band, and now the electricity can flow. Electricity can flow. Not very huge, but very small because very few electrons are able to reach. A lot of electrons which get free at this place, in the bond, are pulled back. It's not easy. The positive ion will pull them back. Another important observation is, so electricity flows. Yes, electricity flows because of the thermal excitation. The temperature has got increased to room temperature. Another important thing which you will see in the case of these situation is that the number of holes that have got created, if you see the diagram very carefully, the number of holes is 2. So 2 holes have got created. Why? Because two electrons two electrons jumped from valence band to conduction band. So in the case of intrinsic semiconductor, whenever you see any electricity flowing because the temperature has gone up, right, from 0 Kelvin to 300 Kelvin, and you see some flow of electricity, always remember the number of holes which have got created is equal to number of electrons. So this is the property of a intrinsic semiconductor, that the number of holes is always equal to number of electrons. All right, so just one more point which is very important. The holes that you see as part of the process which get created because the electrons jump to the conduction band, the holes that you see, okay, let me just draw the holes that I've got created here. These holes also take part in conductivity, which means they also are part of the current flow. Okay, so in an intrinsic semiconductors, the electrons in the conduction band, which is the electrons which have reached here, they also help in electricity flow, and the holes which are left behind in the valence band, they also contribute to the electricity flow. This is very important for you to understand that both electrons and holes are contributing to the flow of electricity in an intrinsic semiconductor. And you can see now that the electrons are in the conduction band in the diagram number 2. So this is your diagram number 2. This is your diagram number 2, and your diagram number 1, which is the energy diagram number 1, had no electron in the conduction band. So I hope you got some sense of how the conduction happens in the intrinsic semiconductors and what happens. I will bring out more videos, short videos, to make you understand all these phenomena in a very simple manner. No channel in the country, no application, no YouTube channel, nothing will explain you the physics of the class 12th and 11th in such a lucid and easy manner, sitting at the comfort of your home. You don't need to go anywhere. Just listen to these lectures. I have 2000 videos already on my YouTube channel. Listen to them. All are very conceptual. A lot of solved numericals on almost every topic. And I keep on bringing these short topics also to refresh your concepts on the individual topics. These are brief ones, but they will help you immensely gain new perspective, new insight into the each of the chapters. So thank you very much for your time, and please wait for my next video. Lattice. Okay, so this is lattice. So everywhere you go, so this has 4 electrons, and you can see this is creating bonds in the neighborhood with the neighboring silicon atoms.